And welcome back, students, as we get into our final topic here in this first semester of Programming 3, and that is of trees. Specifically, we're going to be looking at binary search trees. So, getting started with our final lesson here, the tree data structure is an example of a more complicated data structure made with links. We've already seen some simple ones. We looked at linked list data structures. We kind of briefly glanced at hash tables. But now we're going to get into the binary search trees. So trees are actually a very important and widely used data structure because of their efficiency. So we're going to kind of briefly outline the general techniques used to construct and then to manipulate trees. We're not going to spend a lot of time on them. Same thing with hash tables. We kind of just glanced over them for this semester. But we're going to take that time to at least introduce those concepts to you. So when we look at binary trees, a tree, of course, is a data structure, as we mentioned, and it's structured similar to the diagram shown here at the right. So you'll have a root, and then, of course, you have your node, which, of course, you can see branches off and always into one or two directions. So in a tree, you can reach any node from the top, or the root node, by some path that follows the links. You'll note that there are no cycles in a tree. Unlike with linked lists, you have to, you have to traverse it. You don't necessarily have that same thing here within a binary tree. So if you were to follow the links within a binary search tree, eventually you'll just reach an end. So you reach an endpoint. You notice that the pointers there are null. So a definition of how we actually were to structure up this tree is, let's look at an int one, for example. So this bit of code here, this little snippet, is simply just a structure for a tree. And you can see it's very simple. We have a public class int tree node, private int data, private int tree node left link, private int tree node right link, and a root. That's it. It's very simple in terms of its construction, but it's a little bit more than what we used to have with like maybe a head and position node. You'll notice also that each of the nodes has two references to other nodes, or two links from the binary tree coming from it. This sort of tree, of course, as I've already mentioned, is a binary tree, because binary meaning you have 0 or 1, so you have two choices. Each of the nodes has exactly two link instance variables. Now, there are other kinds of trees with different numbers of link instance variables besides binary search, but the binary tree ultimately is one of the most common cases that you're going to see. All right, so let's start off by examining the tree, starting off with the root node. The instance variable named root serves a purpose like that of the instance variable named head in a linked list. The node whose reference is the root instance variable is obviously just called the root node. Any node in the tree can therefore be reached from the root node simply by following the links. All right, then you have the leaf nodes. Well, the term tree, as we think about this, if we look at our diagram, might seem like a bit of a misnomer because you have like one thing at the top and it gets wider as it gets down. Well, the root is the top of the tree from what we're looking at, and the branching structure is more like a root branching out than a tree. Well, if you really want to think about it, turn that tree upside down and it looks more like a traditional tree, because then you have the trunk and the branches all spinning out. So kind of keep that in mind if you're trying to struggle, like this doesn't look like a tree. Flip the diagram upside down. So the root node would be like where the root structure is, the tree's trunk, and then the leaves are what branches off of that. So those leaves are the ends of the branches that have the link instance variables that are both set to null. And that kind of makes a little more sense because the null is the ending. All right, if you think about a tree, like when we draw out a tree, for example, we typically put the leaves on the very end. Well, the leaves are the very end of that tree structure then. By analogy to an empty linked list, an empty tree is denoted by setting the link variable root equal to null. So if there's nothing in there, root is null. All right, this is something that you're going to love. If you thought you got away from recursion, guess what? It's come back, because recursive trees is a real thing. You'll note that with trees, they have a recursive structure. And that's part of the reason why recursion is so important in programming. If you can understand recursion, you're golden, because a lot of trees will use a recursive style mechanism for their invocation and calling. Now, each tree has an effect to subtrees whose roots are the nodes pointed to by the left link and right link of the root node. So if you look at that first root that we had, it branched off in two directions, has two subtrees, and then those trees can each branch off, etc. This natural kind of recursive structure makes trees particularly amenable to recursive algorithms. So if you want to write a really good binary tree, recursion lends itself really well to a binary tree. For example, consider the task of searching a tree in such a way they visit each node and they do something with the data in the node, such as writing it to the screen. All right, so in order for us to kind of grasp this, we're going to kind of look at this in a general processing order. So how does this algorithm actually process the data now that's being handled? So we're just, we're going to first node and then write it to the screen. So the first thing is pre-order processing. So first thing it wants to do is process the data in the root node. So because it has to start at the root. Kind of like with a linked list, it has to start with the head. Well, it's got to start at the root. Then it's going to process the left subtree because it's going to look at the left side first. Then it's going to process the right subtree. You're going to obtain several variants on the search process by varying the order of these three steps. So pretty much it's always going to come back to, go to the root, look left, look right, root, left, right, etc., etc. So once it's actually obtained, the tree, we get into in-order and post-order processing. Well, in-order processing is, we're looking at those subtrees. We're going to process that left subtree now. All right, then we're going to process the data within the root node. Then we're going to process the right subtree. Then we do post-order processing, where we process the left subtree, process the right subtree, and then process the data in the root node. You'll notice that those are very similar, except in the order where we process the data within the root node. All right, so with binary search trees, there is a storage rule. Pretty much all the values in the left subtree are less than the value in the root node. All the values in the right subtree, therefore, are greater than or equal to the value within the root node. So it's kind of acting as that 0 point, the balance point, if you will, between those two pieces. This rule, therefore, applies recursively to each of the subtrees. So the base case for recursion, of course, if you remember, is an empty tree, which is always considered to satisfy this rule. So we don't have to worry necessarily about an else case here because, well, if there's an empty tree, it's just empty. There's nothing in it. Now, a tree that satisfies the binary search tree storage rule is referred to as a binary search tree. You'll note that if a tree satisfies the binary search tree storage rule and you output the values using the in-order processing method, so remember that was left, I think it was left, data, and then right, then the numbers will be output in order from the smallest number to the largest. For the trees that follow the binary search tree storage rule and are short and fat rather than tall and thin, the values can be retrieved very quickly using a binary search algorithm that is similar in spirit to the binary search algorithm that we examined in programming 2. And when I'm talking about short and fat trees, that means that your trees have a lot of branching outwards to different paths, but they don't necessarily reach down into multiple different levels. So you might have a lot of splits, but you don't necessarily have a lot of your tree. If you were to flip it upside down, it's not tall. It's short, and it's really fat. All right, just think about it. It's better. It's hard to describe without making a visualization. So if you had a tree, and you were to flip that tree, if that tree, when you mapped out all your nodes, was short and fat, she's going to be efficient. So the topic, though, of searching and maintaining a binary search tree in order to realize this efficiency is kind of a little bigger topic that goes beyond what we're going to discuss for this course right now. So, don't worry about the nuances of whether it's a short tree or fat tree or if it's a tall or thin tree, because for our purposes, we're simply just introducing right now this idea of what a binary tree is. However, in order for us to understand that, we need to look at an example that's going to satisfy that storage rule. So, in our example, we have this thing called intree. So that's a class that is for a binary search tree. This satisfies the binary search tree storage rule. Now, for simplicity, this tree will store integers, but a routine modification can produce a similar tree class that stores objects of any class that implements the comparable interface. And of course, we have a binary search tree demo, which demonstrates the use of that tree class, which we'll look at here at the end of the notes. You'll note that no matter which order the integers are inserted into the tree, the output, which uses in-order traversal, will output the integers into sorted order. Now, the methods in this class make extensive use of the recursive nature of binary trees. If a node is a reference to any node in the tree, including possibly the root node, then the entire tree with root a node can be decomposed into three parts. You have the node a node, the left subtree with a root node a node.leftLink, and the right subtree with a root node a node.rightLink. Now, the left and right subtrees do themselves satisfy the binary search tree sort rule. So it's natural to use recursive to process the entire tree by doing the following. Process the left subtree with root node a node.leftLink, process the node a node, process the right subtree with root node a node.rightLink. And you'll notice here what we're using is in order traversal. So off we go. All right, and as I just mentioned, we did the in order traversal after the left tree. This process, by doing in order, will guarantee that numbers in the tree are output in the order smallest to largest. Because if you remember, the right subtree has to be values that are greater than that of the root. Now, the method show elements in subtree uses a very straightforward implementation of this technique. Now, other methods are a little bit more subtle in that only one of the two subtrees needs to be processed. So, for example, consider that method is in subtree, which returns true or false depending on whether the parameter item is in the tree with root node subtree root. So to see if the item is in any place in the tree, set subtree root equal to the root of the entire tree, as we did in the method contains. However, to really express our recursive algorithm for in is subtree, we need to allow the possibility of subtrees other than the entire tree. Now, the algorithm for is in subtree is expressed in pseudocode is shown on the left. So we have here our if the root is empty, we're going to return false. Otherwise, if it contains the item, return true. Otherwise, if it is less than the data, we're going to say that the result is going to have to be obviously in the left link. Otherwise, if it's not, it has to be within the right link. So this is how we branch between these two subtrees. Now, the reason this algorithm gives the correct result is that the tree structure that we have satisfies the binary search tree storage rule, so we know that if item is less than subtree root.data, then the item is in the left subtree, if it's anywhere within the tree, that is. And if item is greater than tree subroot.data, then it's in the right subtree, assuming that, again, it's within the tree. Now, the method with the following heading uses techniques very much like those that's used in a subtree. Private int tree node, insert in subtree, int item, int tree node, subtree root. However, there is something new that we want to look at. When we want the method insert in subtree to insert a new node with the data item into the tree with the root node subtree root. But in this case, we want to deal with subtree root as a variable and not use it only as the value of the variable subtree root. For example, if subtree root contains null, they want to change the value of subtree root to a reference to a new node containing item. However, one thing to consider is that Java parameters cannot change the value of a variable given as an argument. It doesn't handle it like that. So we have to do things just slightly differently in order to really address this problem. So to change the value of the variable subtree root, we return a reference to what we want the new value to be, and we invoke the method subtree root as follows. Subtree root equals insert in subtree, item, comma, subtree root. This right here helps explain why the method insert in subtree returns a reference to a tree node, but we still have to kind of explain why we know it returns a reference to the desired or modified subtree. You'll note that the method insert in subtree searches the tree just as the method is in subtree does, but it does not stop if it finds an item. Instead, it's going to search until it reaches a leaf node, or in other words, a node that has a null pointer. This null is where the item belongs in the tree. So it's going to replace null with a new subtree containing a single node that contains that item. Now, you may need to think about the method insert in subtree a bit to see if that works correctly. So allow yourself some time if you have to study the method insert in subtree, and be sure you're convinced that after the addition, like the following, subtree root equals insert in subtree item common tree root. The tree with root node subtree root will still satisfy the binary search tree storage rule. All right, now that's enough to talk about some of the nuances about how it works. Let's actually talk about the efficiency, because we said, hey, they can be really great. Well, how great can they be? Well, when you're searching a tree that is as short as possible, in other words, all paths from root to a leaf differ by at most one node. The search method is in a search subtree, and hence also the method contains, is about as efficient as the binary search on a sorted array. This really shouldn't be a surprise because, well, the two algorithms that we're going to use to search are in fact very similar. In big O notation, the worst case running time is big O of log n, where n is the number of nodes in the tree. And if you remember, a logarithmic approach to searching is very desirable compared to like a linear or a quadratic. This means that searching a short, fat binary tree is very efficient. So in order for us to obtain this efficiency, well, the tree doesn't actually have to be as short as possible, so long as it comes to being as short as possible. So you don't have to go out of your way to make sure it's short and fat, but you want to try and make sure that your algorithm that you're designing lends itself towards that kind of style. As the tree will become eventually less short and fat and tall and thinner, well, your efficiency is going to start to fall off. In more extreme cases, the efficiency is the same as searching a linked list with the same number of nodes. So, worst case, binary tree pretty much has the same efficiency as a linked list data structure. Not the end of the world. Now, maintaining a tree so that it becomes short and fat as nodes are added is a topic beyond the scope of what we have room for within this course. Now, we will note that only if numbers are stored in the tree in a random order with a very high probability the tree will be short and fat enough to realize the efficiency discussed within the previous text here. Okay, and now that I've traversed through all that, let's go and look at our code. Okay, so here, of course, I have my int tree, and you can see I have my different methods here. Here, of course, is the tree node itself with its inner class. Here's my private tree root. Here's the actual int tree with root being set to null. Here's my insert. Here's my adding, my contains, my show elements. Here's the actual method. So here's my insert in subtree. And you can see here's our looking to see if it is, looking pretty much to see if it's at root. There's left link, right link. It's going to look in there. And of course, if it's in the if it's actually in there, we of course are looking to see if it's in root, if it's true or false. Otherwise, we're going to look in the left link or the right link. And of course, then the show elements is simply just the in order traversal that we're using in order to, in this case, simply just print out those elements. So you can see we have a print command right here. So let's see how this is in action by looking at a simple code. So we have a few lines of code here. So I have an int tree goes int tree. Please enter a list of non-negative integers, place a negative number at the end. So we're using a negative integer to act as a sentinel value in order to terminate a list. All right, then we're going to feed in that list, and then once it's done, we're going to print out in sort of order. So if I run my program, let's just put a couple numbers here. Let's do like 1, 5, 81, 46, 14, 55, and 3. Those are pretty good out of order. And let's do negative 2. Doesn't really matter, as long as it's negative. Hit enter, and you can see that the numbers are now printed out within sorted order. 1, 3, 5, 14, 46, 55, and 81. A pretty quick and easy search return there. And of course, that was all handled here within the tree itself. All right. So with that being said, folks, that wraps up what we have to talk about within this semester. And I'm really excited to get into what we have for the next term. So I will see you next time.